All right, good evening, class. So let's get started. Okay, so let's try to review what we have learned so far. Okay, the second part is about the control system design, right? What is a control system? Whenever you want to improve the performance of the system, right? Control system will be a good approach. So you want to improve the performance of the system, right? For example, right, if you want to, keep the temperature of this room at some comfortable level, right? So you have to change something. Of course, well, there are many examples in the real world applications. You need to observe the output. That is the something you want to change, right? And the input, that is something you can apply directly. You can manipulate. And the desired performance, the reference, that is the desired output you want the system to have. Okay. Very importantly is the key concept for this control system design, or the fundamental principle, is the feedback. So you need to measure and then compare with the desired output, and then you try to minimize the error. Okay, so it's a very simple idea on feedback. That's because that's what we know, how the humans make decisions. We have to know, right, what is happening in our environment, right? We cannot blindly make some decisions, right? You have to know what is going on right now. That is the meaning of this link. You measure the output. Without knowing the current situation, you may make a very wrong decision. Okay, so from this kind of common sense, right? Control theory basically, right, is built upon this common sense. You have to use feedback. Okay, and we discuss all the components, right, for the control system design. Of course, also you have the opportunity to design control systems, right, in your mini project. The first, how do we specify the desired output or the reference signal, right? For project control problems, some of the desired performance requirements. Okay, so many times those requirements are specified very easily from the step response. Okay, and if a system is a second order system, actually you have this formula. Those are theoretic formula relating those step response indicators to the damping ratio electrical frequency. Okay, okay, once again, so I think for the settling time, right, this one is simple, but here I want to, but some students have some difficulty, right? Probably I already showed you last time, right? For the overshoot, right, you have to look at the maximum value, right, in this direction, right? The maximum value around here, right? Let's say now the steady state is 1. Of course, the maximum value should be over 1, bigger than 1, and the peak, right, value, you take that value, you compute. Whatever happens, this part is not relevant to compute the overshoot. Okay, now then sometimes, right, you may the final value may be below, like this, right? And also there may be something fluctuating before this one, but remember, when you compute the overshoot, you take this one up, because this one is in this direction as the negative, right, in the negative direction. So therefore, you like something below that. That is the overshoot. Okay, so whatever happens, right, This one, you don't use that, right? You only use the value which is over the final value. Is that clear? In this way, you know how to do that. Okay, now. Okay, this one, then you get the reference model, right? From those formulas, you try to get what kind of reference model, right, can produce this kind of step response. And as many of you are working on the mini project, you know, okay, those formulas are only relevant for, can only be applied for the standard second order system. In reality, right, in our mini project, it's a sixth order. Okay, so this is kind of just give you some reference value for your dimensional electron frequency. You have to choose. And also you have to change the positions to make the output meet the performance requirements. So normally, you know, you from this one give you two poles, right? Second order system, but then is a high order system. For example, for the mini project, you have to place other four poles. You just place them far away from the dominant one. Okay. So, and then when you try to fine tune the poles, mainly you need to fine tune the dominant complex pair of poles. Okay. And then, so after you have decided the desired poles, okay, you get the characteristic polynomial, right? I just put those poles together, right? Those factors, multiply them together, right? This is would be the closed loop characteristic polynomial. And then we have our pole placement problem to solve. The original plant system here is described by this ABC. Then you apply a state feedback. Because of the state feedback, you can say the system metric has been changed from A to A minus B times K. K is the design parameter, right? You can choose. Then you say, okay, the mathematical question becomes, given A, B, right? And then how are you going to choose K? Such that the correct polynomial of the system, you know, match the desired one. Okay. And we first derive the solution for the single input, single output system. For this one, we have a very clean and simple solution. Okay, so in this case, because the single input, so the input is a scalar. Therefore, your R is a scalar, then this K will just be a row vector. All right, and then what is the condition? So we say it has to be controllable. Then the poles can be placed to anywhere you like. Then we can derive the Eichmann's formula. And how did you do that? Right, we use the controllable canonical form to easily, right, come up with a solution. Okay, then you can apply the Eichmann's form for single input system. Okay, so here apply this formula, right? This is controllability matrix, this is vector, but here the meaning of this phi d s is the desired characteristic polynomial, right? Just to put s equals a, you compute this phi d of a. That will be our matrix. What if you forget? Of course, you know that you have the help sheet, right? You are not going to forget. But anyway, this is one way to solve the pole placement problem. The other way is that, okay, you don't need to remember the Eichmann's formula, right? You can do it by direct comparison. You get the closed loop polynomial of the, right? In this way, determinant of this matrix. Of course, K will be the design parameter, right? You get a polynomial. The coefficients of those polynomial will depend upon the parameter. Then you match the coefficients of the desired polynomial. You will get a number of equations and then you solve them. That is the other way to solve the pole placement problem. Okay. Now for the single input case, how many solutions can you get? Of course, right now there is only one solution. Okay. Now, then for the multiple input case, right? This is the case we're going to handle for the mini project. Okay, so in this case, U is a vector, now K is a matrix. If the system is controllable, the poles can be placed anywhere. So we have the same condition, but the main difference is this one. Is the solution unique? Right. Now you say, if you are, this point has been very clearly demonstrated. It's not unique. If you are doing the video project, you will find that if you use the place, if you use the Ackermann, in MATLAB, their solutions are different right from yours, although they have the same desired pose. Okay, now, first of all, there are many ways to understand why the solution is not unique. The simple way is to, if you try to compare the coefficients of those two polynomials. Okay, there will be n equations, right? There are n coefficients to match, but on this side, the k, the design parameters of this k, there will be n times n. So there are n times n parameters on the left side, but there are only n equations. You have more design parameters than the number of the equations, right? So you can just understand in a very simple way. You will not get just one solution. If the k is a vector, then you only have n design parameters. That can explain for the single input case, you only get one solution. Okay, so that's one way to understand why the case why you have multiple solutions. We just understand it in an algebraic way. Right. Now, also, for many of you who are doing the mini project, you should know the answer. Right, different solutions actually they all give you the same pose, but will they give you the same step response? Of course not, right? If they give you the same step response, why do we spend time, to talk about different ways? Definitely, right? Different solutions that will give you the same pose, but will need two different zeros. Okay. So therefore, when you solve the pole placement problem, right, it's not only the desired pose matters, it is also the pole placement method you are using can have some impact on your final result. Okay. Now, how do we solve this pole placement for multiple input system? Right. One simple way is that because you are familiar with the simple method for the single input case, you try to convert it into a single input case. So you force the input as a weight vector, q is fixed times a scalar, right? Then you merge those b times q as one vector, b. Okay, and as long as this b times q, right, this one and a, this pair ab is controllable, then you can just use any single input pole placement problem to determine the weight vector k. But the final answer, right, will be a matrix, will be just q times k transpose. So this is one way. We know, of course, if you do it, the algorithm is simple to compute, but does not, because it does not fully exploit the freedom of the input. So normally the performance will not be good. Okay. Then there is a third way for the pole placement. Is the forerun who are trying to exploit the freedom of all the control inputs. You're given a controllable AB and also the desired parameters polynomial you want to match, right? Okay, for this one, we need to use the controllable canonic form for the multiple input case. Okay, to compute this controllable canonic form, the time-consuming part will be computing the transformation matrix T. Once you get the correct, right, transformation, the others, right, you just follow the procedure step by step. Okay, then you get your T and then you will get your A bar and B bar. Okay. Now, here, you know, let's say when you try to, if you use your, you know, you try to get the solutions for some questions, right? Easy way to verify whether the T is correct or not, you look at the form of your A bar and B bar. The trivial, right? The trivial rows must match each other, okay? Right, we know those trivial rows, which means that the A bar, in those rows, there will be only one value of 1, the others will be 0, right? Then for those rows, the corresponding row in that control vector, those should be 0, which means the control input cannot affect those trivial rows. So that's an easy way to check. I suggest you should check. You check your A bar and B bar. If those trivial rows cannot match, it means, right, something is wrong with your T. Okay? Okay, how do we get the T? You first get the controllability matrix. This one is straightforward, right? You learned that in part 1. That's how you can check the controllability. This matrix has to be 4 rank. If it is not 4 rank, of course, it is not controllable. Okay, if it is controllable, then you have to select A independent vectors. For single input system, of course, the controllability matrix is a square matrix, right? All the vectors are there. That one is straightforward, okay? But for multiple input case, right, there are many ways to get the combination of the vectors, but you are supposed to obtain these independent vectors in a strict order from left to right. Okay, you cannot just get any combination. You have to follow the order. Okay, because why are we doing this? Because we want to assure that all the inputs will play a part in the placement. After the vectors are selected, also the next step to form the matrix C is important, right? You have to reorder those vectors in this matrix WC. Okay. Remember, in this matrix WC, right? This order will be B1, B2, B3, right? And then AB1, AB2. You can see the sequence is different from this one. That one you have to be very careful. If you don't get this right, the rest are wrong. The rest are wrong. Okay, you can say, but we need to rearrange that such that all the vectors associated with B are grouped together. Also follow a strict order, right? In terms of the matrix A, so it should be B1, A1, okay? And then the next one will be B2, A times B2, right? And then the other ones, the main point is that you have to regroup the vectors, okay? In this one, then you count how many vectors are related to B1, right? There, in this way, there are D1 of them, not the meaning of D1. How many vectors are related to B2 in this matrix? That's the meaning of D2. All right. Any questions? I think some students made mistake there. But I think in the tutorial problems, right, it is clearly formulated in a proper way. Okay, so this matrix, you have to get it right. If you don't get it right, the rest are wrong, right? Okay, now, once you get this one in a proper way, then the rest, right, the rest will be straightforward. You can just compute the inverse of C, right? And then For multiple input case, right, we need to take out m rows because there are m inputs. For a single input case, right, you only need to take out one row, right? one row in from the inverse of C. Okay, but now this is the way you say, okay, you first look at D1, right? That is the number of the vectors which are associated with the input. For the single input case, where of course D1 equals n. So you just take out the last row of this matrix. But then there are multiple of them. If there are multiple of them, right, then you need to take out m rows, right? Those, how do you take out them? It depends upon those D1, D2, right, and D3. Okay. And then once you get those rows, you can construct all the other rows. You will get a m by m matrix. Okay. Any questions on how to construct T? Remember, okay, in your mini project, right, you are supposed to compute all those matrices and the vectors step by step. You cannot say, okay, I use place, right, to do it. Okay, here, once you get T right, actually you can't get your B bar. Remember, your B bar has to be in this form. For all those trivial rows, all the values should be 0. There are only m rows. There are only m rows with non-zero values. Those are the non-trivial rows. Those are the rows which can change the matrix A. The other rows, the values should be 0. You should check that. If you don't get the correct one, right? Of course, something is wrong in your calculation. You cannot just go ahead and you get some wrong values, and then you still try to compute the rest, because at this step you already made a mistake if your B bar is not in the proper form. Okay. In MATLAB, remember, you are not going to get a perfect 0, right? It's not exact 0. Could be 10 to the minus 10, 10 to the minus 14. Remember, all those numerical calculations, they carry some numerical errors, right? Okay, those values will be treated as 0. Now, from this whole computation procedure, how many T can you find? There are multiple ways to get the T, or there is only one transformation matrix you can get. There is only one. There is only one way. Okay. From all those steps, there you follow strict order, right? Constructing C, right? And then of course there is only one way to get the C inverse, and also there is only one way to construct the T. So far there is only one solution to get the controllable kinetic form. Okay. Now you specify a desired closed loop matrix AD. Those AD will be in a controllable kinetic form, right? They will match the same form as that for the controllable kinetic form of the system, except those non-trivial rows. So the trivial rows must be the same, because your controller cannot change those trivial rows. They're completely fixed, right? But for the non-trivial rows, you can specify the values. So here is the key point. How many ways can you choose the desired closed loop matrix? The controllable kinetic form, the desired controllable kinetic form. How many ways can you construct? There is only one, right? I also show that there are multiple of them. Sorry, there are multiple of them. It depends upon how you construct the subsystem. I showed that in my lecture notes. Also, this one, there are many ways. So therefore, even though you use the 4-rank method and then you use a different way to get the desired controllable kinetic form, your result, right, the step responses will be different. Okay, that's why I'm saying when you try to meet the performance requirements, not only the desired pose matters, also the way you specify your closed loop, right, matrix will matter. Okay, from the student's experience, right, a good way is that you split those AD into two subsystems, third order and third order. That one probably give you a better performance than you put all of the, I mean, it's like you do it in another way, right? You put all the values at the last row. Okay. Okay. So once this one you get, okay, and then compare the non-trivial rows of the closed canonic form with the desired one. In this one, you will compute the K bar, right? You compute that, you get the K bar. Of course, once this KAD is chosen, in this step, right, there is also just one solution. Okay, finally, you get this K. So the computation, of course, is much more complicated than the unique rank method, but you can fully explore the freedom of all the inputs, so therefore the overall performance normally is better than the unique rank method. Okay. So for the mini project, I believe most of you are using this one. Okay. Now, because also the parameters of the project are based upon your matriculation number. So also depends upon your matriculation number. For some students, they may even get a good performance with unity with a simple one. Okay, but I think the majority of you should follow the 4-rank method to get a good solution. Okay. Now, then that is the topic for the power placement, and then we say, okay, for the power placement, we only focus on the transit performance requirements, right? We didn't care about the size of the control signal, but in reality, we have to strike a balance between the speed and the cost. So that's the motivation behind the optimal control. Okay. So we have to put a penalty for both the state vector, right, and also the cost for the control input. You have to specify the Q and R. We try to minimize this. And turns out this will be the form of the controller to achieve this. So we still use our state feedback. And then what are the conditions? First of all, right, the system has to be controllable. So what would happen if the system is not controllable? Okay, if the uncontrollable mode is unstable, right, the unstable mode will blow up. Okay. The second assumption is that AH is completely observable, where H is kind of a square root of the matrix Q. So why do we need this condition? Is that we'll make sure that there are some state variables are included in the performance index, right? Otherwise, right, those state variables which are not connected performance index may blow up. Okay. Then the third condition is that the matrix R has to be positive definite, while this matrix Q is semi-positive definite. So what would happen is R is not positive definite. It means some of the inputs may not be considered in the cost function, and then the value of those inputs may also go to infinity if you try to minimize the cost function. You can imagine, of course, if you can apply an input with the magnitude of infinity, it means, right, you can't do anything, right? You can't do anything. Of course, that is not right. That is not realistic. You cannot do that. Okay. How to solve the AQR problem, right? So we say this one actually How do we compute K? Very easily, right? This is the formula for K, but the problem is what is the matrix P, right? So the key part for the solution for the LQR is this matrix Riccati equation. So you have to find out a solution which is a positive definite from this equation. So how do we solve this? Okay, therefore the lower order system, right? I first assume a matrix P with symmetric elements, right? And then you plug it into this equation. Okay. It normally will give you a set of nonlinear equations with multiple solutions. But among all those solutions, there will be only one which will satisfy the requirement that the matrix P is positive definite. Okay, you can get one. But in this way, of course, it is not very straightforward, right? It involves nonlinear equations, and also you have to select one of them. Okay, so there is another way to do it. Is you form a 2n by 2n matrix, right? Let's say your mini project A equals 6, so you are going to get a 12 by 12 matrix, and all those matrices are given. And for this matrix, of course, it has 12 eigenvalues, right? You just find its stable eigenvalues. There are unstable eigenvalues, and the other half of the eigenvalues are all unstable. Now, for those stable eigenvalues, you find their eigenvectors. Okay? And then those eigenvectors will be two-dimensional, right? So you just split it into half, the lower half and the bottom. I mean, the upper half and lower half, right? This is a n-dimensional vector, upper one, right? V, and then this U is the lower half. You split the one vector into two, okay? And then you can compute the P in this way. And also in this step, right, it doesn't matter, the sequence doesn't matter, right? Okay, but it has to be correspond, right? Let's say this mu1 correspond to v1. If you permute the sequence of these vectors in this matrix, if you permute this one correspondingly, you will get the same answer. Okay. Now, then the third topic we talk about is about the server control, because both the power placement and the LQR focus on how fast we want the system to behave, right? But we haven't solved the problem where how accurate your output can follow the desired output. Therefore, when I say the transit performance requirements, right? Well, I want you to say, okay, those overshoot ratio and also this settling time, we don't care what is the steady state value of those step response, when we try to check that. But finally, of course, we want the output, this to track the desired output when time goes to infinity. Okay, then we need to introduce the server control. We don't just want the system, right, the state values go to 0. So how do we do that? Then we say this one, to achieve this, it consists of two parts. One is stabilization, the other one is servo mechanism. You have to put them together to achieve the goal. Then we present two solutions. For the single input, single output system, right, we can use the output feedback. For the multiple input system, we use the state feedback. Okay, then we'll talk about the polynomial approach for the single input, single output case. Remember, when we're saying that system is a unit output feedback. It means there is nothing there in this feedback loop. We don't model the sensor there. Okay. We have a plant, right? We have our controller. This G is given. You try to design a K. And the disturbance is added here. For this framework, right? For this framework, then we have a very good solution. Okay, then let's try to analyze the closed loop transfer function, right? We say, okay, we get this. This is the form of this plant. This is the transfer function for this controller. N and D are given, right? You are trying to design A and B. We said the order of the process is N, which means the degree of this N, degree of this transfer function is N. We can compute the closed loop transfer function. It will be in this form. So you're given D and N, you try to figure out what is A and B. Then we say, we first have to know how to stabilize the whole system given the transfer function. Okay, we say it means, right, this closed loop polynomial for this transfer function, right, in the denominator of the transfer function has to match a desired polynomial. Of course, this polynomial, all the roots have to be stable. The roots of this, right, the desired one, are the desired goals of the overall system to achieve. And A and B are unknown polynomials for the desired design parameters you want to find out. And first, we have to be very clear about the conditions to solve this problem. Algebraically, it's very simple. Say D and N should be co-prime. They have no common factors. If they have common factors, of course, you see on the left side, there is a common factor. You can take out that common factor, right? Then on the right side, that common factor has to be a part of the desired polynomial. So therefore, that's why we have this condition. If the common factor is stable, we say, okay, then the stable factor will not have a negative impact. But if the common factor is unstable, basically, right, we cannot stabilize the system. Then we talk about the minimum order, right, degree of the controller, right? If the order of the system is N, then we'll say if the order of the controller is N-1, there is only one solution. If the order of the controller is larger than N-1, then you have a infinite sum of solutions. Okay. How to find the solution? Okay, for this problem, right? How do we find out the solution? The direct way is by just direct comparison. You have this D and N, you have this desired polynomial, right? Just plug in A and B with those unknown coefficients, right? Then you compare those two polynomials. The coefficients have to match. Then you get a number of equations. Let's say when you find out the design parameters, the number of design parameters, right, is less than the number of the equations. Then which means there will be no solution, right? You have to increase the order of your controller. Give more freedom. Okay. Okay. That is the way we are going to solve the stabilization. Then the next one is the servo mechanism, right? So we need to understand how can we make the error signal go to 0. Okay. To do that, right, we just need to get the solution in the S domain by Laplace transform, but we get the solution of the error signal. It's just the reference signal minus the output. So we plug it in, right? Then we get this form, the final solution. And then we find out, right, because in order to make this one go to 0, all those factors, right, in those closed loop polynomials that are stable, But there is an unstable factor, right, in the reference signal DR. To make this one go to 0, the only possible way is to make this DR disappear, right? Okay, that's why we need to put this DR as a part of A. A, right, is the denominator of your controller. If DR does not disappear, right, this signal will not go to 0 by partial fraction, right? A partial fraction, you know that there will be a factor corresponding to those unstable poles. Okay. Similarly, if we compute the output due to the disturbance, the output, right, due to the means, right, try to get the output due to the disturbance, right? We get the expression in the S domain, and then we realize, right, it also depends upon this one, the unstable poles of the disturbance. To make this one go to 0, the dW has to disappear. Therefore, we have to also cancel it out. Okay, to make this one go to 0, we have to cancel out dW. So therefore, the way to do it is that to make this dW as a part of A, then it will be cancelled out. Okay, is that clear? So you need to understand the theory behind the algorithm. So therefore, overall, we say we have to include the unstable factor of the disturbance and the reference signal, right, in the denominator of the controller. So that's why, right, we need to get the least common denominator of the R and W. We call it Q. So that is the servo mechanism we're going to use to solve the servo control problem. Okay, so the design procedure, you first, of course, get the transfer function of this plant. Then you determine the unstable factors of the disturbance and the reference. You put them together, right? That's the least common denominator of W and R. Q. So once you have this Q, you form a generalized plant. You put this D and Q together. You try to stabilize this generalized plant. That then becomes a stabilization problem. Okay. Then you design this K tutor to do it. The final controller will be the K tutor times 1 over Q. So from this design, right, we know that Q will be stable by pole placement. And because this Q, right, is inside A, such that, right, the unstable factors of R and W will disappear in the final solution of the output. So in this way, we'll achieve the goal, right, to make the output follow the desired output asymptotically. But the problem with this design is that the order of the controller, right, might be high. Okay, because not only K tutor, right, you have to put this Q into this K tutor. Okay, so therefore, to simplify the design, we have another way. So let's say we have the transfer function. We also have to get the Q. Then we don't get the generalized plant, right? No need to form the generalized plant. You just say, okay, I have to force this Q as a part of A. So put this Q as a part of A. Sometimes you may have to design another polynomial for A. It depends upon the complexity of your problem. Okay, then there are some other tricks, like if the poles of the open loop D, right, if this D already contains some unstable factors of Q, right, you don't need to include them again. Like, if the D has an integrator, and then you don't have to include that integrator again inside A. Those will simplify your calculation. Also, if there are some stable poles or zeros in the transfer function of the system, you may also try to cancel them out. By cancellation, you will have a reduced order controller. Okay, that also can simplify the design. Okay, so if you follow this way, right, there are a number of tricks you have to remember. Then the final solution will be much simpler than the previous one. But if you follow this way, you have to know all the tricks, right? All the tricks. But if you follow the previous way, you don't have to use all those tricks, right? You just do it step by step, but you end up with a complicated controller. Okay, that one normally, right? This way will save you a lot of time if you do it, because the time is precious. You find the exam, you want to save time to get the solution as quick as possible. Okay. Okay, so then finally, right, to solve this placement problem here, you just plug in the polynomial, you compare the coefficients. Okay. Once again here, when you do this, if you realize, right, that the number of the design parameters is not enough, right, cannot satisfy all the equations, it just means that you have to increase the order of your controller. Okay, you can get more design parameters. There is always a solution there, because you can always increase the complexity of your controller. But you'd better start with the simpler one, right? The simplest design, again, will save you a lot of time. Okay? The final part, right, you also make sure that the B over A is proper. The degree of B, right, has to be smaller than or equal to A. The degree of A, okay. Also, this is one common mistake made by the students in the past. There are two mistakes, right? One is that the poles, right, of the closed loop, somehow they become unstable, right? You place the poles on the closed loop unstable values. That is a major mistake. The other mistake is that the final controller is not proper. There is only one exception. You can use a improper controller. That is the PID controller, right? If you say the final solution is a PID controller, I will allow that as the correct solution for PID, because the PID in simplest form, right, is improper, because the derivative term, that term is not a proper transfer function. But since PID, right, is kind of a classical, you have learned that, so I will accept that as a correct answer. Okay, but for other controllers, it has to be proper. All right, any questions? Okay, then for the multiple input case, right? Multiple input case, this one you have to know how to do it, because for your mini project, right, it's multiple input case. You cannot use the single input, single output design. This one consider here M plant, which means that the number of the inputs match the number of the outputs. But then we define this error signal. In this way, we have to use the integrator, right? We introduce the integrator because we know the integrator has a magic power to deal with the constant reference input. Okay, so we have to introduce the integrator, and then we put this integrator, right? Combine the integrator with this state space model. We have a new augmented system. Okay, then you try to stabilize this augmented system. Then the augmented system, right, make sure that it is controllable. Because only when it is controllable, it can be stabilized by this feedback controller. Okay. So for a mini project, right? For a mini project, you first check out if you do it in this way, is the system controllable? If it is not controllable, you try to understand why it is not controllable, right? And then you can figure out a way to make it controllable by change the way, right? By changing the way you construct the augmented system. Okay. Okay, and then so once you have a controllable augmented system, right? The rest, right? You just follow the design for the power placement or LQR, because you have a new system, you have this new ABC, right? And then just do it as one, using the way you have learned. Okay. So once the feedback system, closely stable, we know that if there is a constant input, all the signals will stabilize to some constant, including V. V will be a constant. So therefore, the derivative of this V will go to 0. But the derivative V is the error signal. So that is the magic power of the integrator for constant type of reference signal. Okay. So once again, the design, right, consists of two parts. One is the stabilization. The other one is servo mechanism. The servo mechanism here is that you have to construct an augmented system. You cannot just stabilize the original system, right? You have to add some extra stuff to your system. For constant reference signal, you add the integrator. Okay, that's the servo mechanism. And then the stabilization means you need to know how to stabilize the overall system. Okay, you put them together, you'll get what you want. And that is also the idea. You can deal with other types of reference signal. Of course, we don't have time. Of course, we are not going to examine you that, right? How to do it for other types for multiple input case. Okay, so as long as you know how to do it with the constant case, will be good enough. Now, then the next topic, right, is we know you have learned a lot of things about the design for single input, single output case, but for multiple input case, it's more complicated. So we try to find out a way to simplify the design for the multiple input case. They probably can just first, right, decouple the system multiple input case into a single input case. So that is the decoupling. The purpose of decoupling, such that one input will only affect one output. Okay. Okay. There are two ways. One is to decouple by state feedback. So this is the time where you have to design both K and F together. Okay. Then you plug this one into the system, you get the closed loop. We idealize the transfer function. This is the open loop transfer function, and this is the closed loop transfer function. We know that we want to know how this closed loop transfer function relates to the open loop. So this is the formula. We derived that. Therefore, if the closed loop is diagonal, then the open loop must be long singular. Actually, so that's the only condition for the system to be decoupled. Therefore, we need to find a condition to assure that the open loop transfer function is long singular. Then we say, okay, we partition those C here into M row vectors. Then we define the relative degree for each row, the sigma I. So sigma I, that's the minimum value where you compute the Ci times a to the power of j minus 1. B is not 0. So first you compute C times B. Is it 0? If it is 0, then you compute C times A times B, right? You check whether it's 0 or not. If it is 0, then you compute C to the A square B. In this way, you find out the minimum, right, J, which can make this one not to be 0. That is the relative degree. So sigma I is very important for you to design the decoupling, okay? Because the other matrix will totally depend upon the sigma I in the rest of the procedure. All right, so once you know the sigma I, then we can prove that the G, the transfer function G, can be written in this way. It will be a diagonal matrix times another matrix. Okay, so where those B star and C star will be computed, right, with this formula, where those sigma I are already determined. So that's why I say, how do we compute those B star and C star? It all depends upon the relative degree. So if you get those values wrong, right, you will get a wrong solution. Okay, so sigma I is the relative degree of transfer function for each row. B star corresponds to the leading coefficients of those 0 polynomials. So how do we prove that? We say depends upon the way we express this transfer. This matrix, inverse of this matrix, can be expressed as an infinite series. It's like a Taylor series. Okay. Okay, once we know this B star, then there is another condition. Say this B star has to be non-singular, such that we can compute its inverse. Okay. The C star, it doesn't matter whether it's a singular or non-singular. Okay. Because here in this design, the final answer, the F and B depends upon the inverse of this B star. If we do it right in this way, the final closed loop transfer function will be just integrators. But we know the integrators are not stable, right? Okay, so therefore, can we make it stable? Yes, we can. So we decouple it with power placement. So this is what you have to do this with your mini project. So you have to design this closed loop, those transfer functions. You make them to be stable ones. So you specify those stable transfer functions for each subsystem. Okay, so you have to first design the pose, right? Design the pose for the subsystem. And once you know those polynomial, then it's very easy to compute. Then you say, we still have the same B star. We just need to compute another C star. Okay, here, those C star, right, depends upon this, C times this polynomial. Those polynomials are those stable polynomials. Those are the denominators in those transfer function, right? But you try to just replace those S by A, then you get those values for those function of the matrix A. So those will be the matrix. You compute that, and then you get your C star star. Okay, you can say that in this final design, you keep the same B star, right? And then you just change the way you compute the C star. You'll get your design. Okay. And then there is another way to do the decoupling. if you know the transfer function matrix. Remember, right? In your mini project, you have the state space model. So therefore, you can also get the transfer function. So you can, that's why I say you can either use the state feedback decoupling or use the output feedback decoupling for your mini project. Of course, actually, once you get the transfer function, the solution is even simpler. You have this G, that will be a matrix. You try to design another controller, right? Another matrix K, such that K times G, G times K will be a diagonal matrix. So we will first, get the transfer function of this closed loop, and then we prove that if the closed loop is diagonal, then this G times K has to be diagonal. So that's it. We say, hey, we just try to decouple the open loop. Then we say, how do we design that? We say we split the design of the controller into two parts. One is a decoupler, the other one is stabilizer. So the step one, right, you design the decoupler, right, KD. The purpose is to make G times KD diagonal. And when you do that, right, we say make sure that there are no unstable pole zero cancellation. In this step, right, your KD may be not proper because but you don't have to worry about that because you can't make it proper by the second step. Step two, right, whenever such a KD is found, you already decoupled the system, right? The open loop transfer function already become diagonal. Then for each diagonal transfer function, you just design a stabilizer for each one of them. So your KS will be a diagonal matrix. Okay, then how do you stabilize those transfer functions? You have learned that in the server control, right? You can stabilize it one by one. Each one is just a single input case, right? For a single transfer function. You try to stabilize it. Okay, is that clear? Okay, so loop by loop we do it. So finally, you check this will be your final controller, KD times KS. You put them together. There are two conditions. You try to make sure that your design is correct. Two conditions. The first one, the final answer K is proper. The second one, make sure there are no unstable pole zero cancellation between G and K. If there are unstable pole zero cancellation, of course, you will be in trouble. The system will be unstable. Okay, so if you can imagine, if the original system G, right, original system is stable, actually you will not encounter those unstable pole zero cancellation because all the poles, right, all the factors of G is stable ones, right? If there are cancellations, there must be stable factors cancellation, right? Okay, so for stable system, it is safe to do it, but for unstable system, you have to be careful. So the key step in decoupling control is to find the decoupler, KD. Or can we simply use KD as an inverse of the transfer function matrix? We say we cannot do it as it may lead to unstable pole zero cancellation. Okay, and also the other reason is that because G involves the both numerator and the denominator, right? So actually, if you do this, it may be the final answer may be complicated. Okay, so therefore, we introduce two ways. Those two ways will be simpler than the way, right? You try to do it like this. because sometimes you say when the G is simple and also the transfer function has no unstable poles, this will work. Okay, this will also work. But if it is unstable and also it involves the transfer function matrix is not very simple. Even if you do this, right, your final answer may be more complicated than the other two designs. Okay, in this way, we try to write the transfer function into a numerator part and the denominator part. We take out those denominators. Okay, so therefore we say, hey, we write this G as a denominator, a D. We take out this common denominator. We say that D is the least common denominator. We take it out such that this matrix N will be a matrix with all the elements are polynomials that do not have any denominators. Okay, that will simplify the calculation. Okay, and then you try to compute the determinant of this matrix N. You say, okay, if this one and the denominator of this G will have no common unstable roots, you just simply take this KD as the adjacent matrix of N. Of course, all the elements in this KD, right, will be polynomials, right? They have no denominators because N, matrix N has no denominators. So therefore, normally your KD will be not proper. Okay, and then this will be the result from the decoupler. I would say we have a very simple form for the decoupler result. One problem with this one is that the order of the decoupler system is large. So the refinement, you say, okay, when you try to express those G, we don't use the least common denominator. We take the least common denominator row by row, right? And in this way, we can also write out the G as a matrix times a matrix where this is diagonal matrix, right? But this NR is a matrix where all the elements are just polynomials. That's another way to write this transfer function matrix. Okay, and then we just design the decoupler, right, as the adjacent matrix of this NR. Okay, in this way, you say once you know how to write this NR, right, in this form, it's very easy to compute the adjacent matrix. So therefore, it's very easy to get this one. Then you have this diagonal matrix. The system is decoupled, but it is not stable normally, and also the KD is not proper, right? You have to get the second step, design the stabilizer to stabilize each open loop and also make sure that the final controller is proper. Okay. Now, the final subject is the state estimation. We know the state space approach uses state feedback, but we need to know all the signals for the state vector. But in reality, right, X is not available. What we can observe is the output. So to implement this controller, so we need to know the state vector. So therefore, we need to estimate that. The fourth order observer is that, okay, we try to introduce the feedback term. So we know for observer design, we need to know the model of the system. Okay, so we build the model, right? Use the original ABC, but we include a state feedback mechanism. We use the difference between the output and the estimated output, right? And then we say, with this simple feedback, we can make sure that the estimation error will go to 0. Okay, so this is the equations for the observer. And when we try to analyze the estimation error, we realize what we need to do is to make this A minus L times C stable. Okay, so the way to solve this problem, you use a pole placement algorithm to obtain those errors. Okay, here in the design examples, right? In the design examples, I use the direct comparison, right? We say I just try to get the determinant of those SI minus A minus LC. This is the direct comparison method. Equal some polynomial. Right now, for your mini project, right? For your mini project, this one you cannot do it in this way. You cannot do it in this way. That one will give you, it will be very complicated. So you follow the other way. But when you try to follow the other way, just remember, you just follow the way for the controller design. But remember, so which means you have to, well, this way corresponding to H transpose, remember, this one corresponding to C transpose. Then you try to compute your K tilde. You just treated it as another control system. You try to stabilize it. Okay, you use all the way you have learned, but just remember those correspondence. So finally, those K tilde will not be error. Right, this one will be error tilde, error transpose. So those K tilde you get is the error transpose. So remember, when you try to get it back, you have to do the transpose. Okay, is that clear? So that is the dual property. So you can convert the observer design to a controller design. Okay. Any questions? Because some students send me email, right? They have some confusion. So once estimate available, okay, so you know how to estimate the X height, then this will be your final controller, right? You use estimated state. And then we also introduce the reduced order because we know, hey, let's say I already know M outputs that correspond to M state variables, right? So we don't have to estimate them again. We just need to estimate the rest of the state variables, which there are M minus M state variables we try to estimate. So we define a transformed state, right? Which Kc is the T times X, but Kc is M minus N, right? There are those are the state variables we try to estimate. We put them together, right? Y, we combine those Y and Kc. So this will be the transformed state vector we try to estimate. Okay, then matrix Ct has to be non-singular. Now, the key in this reduced order observer, you have to use T as a design variable. There are infinite number of ways to construct this T that will give you the power to design the reduced order. You don't fix your T at the beginning. Okay, then you say I will have to, I cannot use the original ABC again directly, so I have to construct a new model for the observer. So you have to design the D, E, and G. We know the observer will depend upon the input and output. Okay, we say, okay, this is objective. I try to make the Kc go to T times X, right? Then we analyze the dynamics of the error vector, right? We say, okay, this is the dynamic equations for them. Now, if D is stable, and if we make this term go to 0, and this term go to 0, so we'll get this one. That is the way we make D go to 0. Right, okay. I think at some point our students said you make D equals 0. Remember, how you make those equal to 0? You cannot make D equal 0. Okay, you have to just make the D to be stable. Okay, if make D equal 0, right, the D E will not go to 0. E will go to a constant. Okay, and then we say, okay, the design procedure is simple, but the answer, right, will not be unique. So you first choose, okay, you get the constant on T, you say, okay, this matrix has to be non-singular. And then you just choose your stable matrix D. Okay, once you fix the D, right, and then you solve this equation. The solution to solve this equation always that the number of the design parameters is more than the number of equations. So there are infinite number of them. You choose the numbers which are simple to compute. Okay, you choose 1 or 0, right? Basically, for some of the, you fix those some numbers to be 1 or 0, right? And then you try to solve the rest of the equations. That's the easy way out. And then finally you get the T, and then you can get your E. Okay, but don't forget, so if you are supposed to design a reduced order, don't forget the last step. You say, okay, once I have Y C, and then this is the way I construct the state vector, because this X height, that will be the vector you are going to use in your controller design. All right, I think let's have a break. Let's have a break. Now I will do the break of the project. Let's have a 15 minutes break. All right, let's talk about the project. Okay, let's first say how do we design a control system for real applications like what we are doing for the mini project, right? The first step, actually you have to build the model of the process. If the system is nonlinear, you have to linearize the model around the operation point, right? You try to get the state space model. Remember, all the methods we have discussed is for the linear system, right? But remember, that does not mean that for nonlinear system you cannot apply. For nonlinear system, the simplest way, right? You try to linearize it around the equilibrium point. As long as the deviation is not big, right? You still have a good model. But of course, to get the original state space model, right? The original nonlinear model of the plant, that one, in many problems, that could be the most challenging part. Because once you have the model, there are many things you can do, right? But how do you get that model first? Okay. Of course, nowadays, people also have some way. If you don't have the model, you have this model free, they can build a black box model with AI. But that is there's some research, very active research done in that direction. Okay, step 2. Once you have the model, you first you try to design the controller, right? Assuming that you have all the information about the state variables. So you don't have to worry whether you can measure the state variables or not. You first assume you have the perfect information. Then you try to make it work. Right? Okay, then step 3. Then you have to decide what kind of output you want to observe, right? You want to, that depends on the budget. Then you decide, how many outputs you want to measure. Okay, of course, if you are very short of money, right, you want to just get one output. And for the state estimation. Okay, for real application, a common filter should be used. But in this course, right, we don't have time to cover the common filter. But no matter what your the budget is, you have to get one output, right? Otherwise, there is no feedback. You have to know what is going on, right? You have to get one output. Then step 4, you replace those state variables with their estimates and implement the controller. You need to build an observer to estimate all the state variables. Okay. Okay, and then the 3 factors when you design controller in reality. Of course, the speed, right? You look at the transit response, then the accuracy, right? The steady state error, and the cost. So there is a balance, right? If you want to be very fast, normally the cost is high. So there is a compromise you have to make. Now, this project, right, is about a self-balanced two-wheeled vehicle. This is a real-world applications. Let's first take a look at the video clip.
We're taking smartphone, spaceship technology on a motorcycle platform with the safety of a car. Basically, it's a robot motorcycle. It self-balances and really increases your safety and your range and the excitement of riding a motorcycle. 200 miles per charge. It's a 2-wheel drive, wheel hub motored, electric vehicle. Steer it like a car. You sit in it like a car. You have pedals like a car, but the robot side, it takes your steering input and leans you into turns, a lot like a jet fighter. So as you can see, full electronics in here. And this is actually our real gyro right here, if you want to take a look at this. The gyroscopes inside basically output around 1,300 foot-pounds of torque. So you basically need a baby elephant to knock it over. It's a lot like a CMG or a control moment gyro. The International Space Station and most satellites use the same orientation technology. We've just kind of taken that and made it commercially available. There are servos and there are gyro motors, there are traction motors, but sensors like an IMU, IR sensors. There's actually a lot of temperature and heat sensors, a myriad of sensors that actually all feed data, and that has to be processed. And through that process, a command to the gyros to tilt and lean the vehicle to keep it balanced or either to lean into a turn. All, it's very dependently based on our processing system. The prototype that we have now uses 2 i7s. At our end product, we should be using something that would power a smartphone today. One of the hurdles in our development is having the vehicle actually be more aware of its surroundings. So it's kind of like putting AI, but also having good sensory perception of the road, of any kind of external influences or disturbances, and having that all get computed and processed to allow for stability in all scenarios. On the heads-up display, you can see battery life, range, how much left you have in your possession budget. It's kind of like your artificial horizon. And also, it's basically a rolling smartphone, so all of the information on your smartphone will be on a side panel. Upgrading the hardware, the gyro can be done pretty easily. The gyros actually come and the battery pack come in its own modular unit. So you can upgrade the gyro output, you can upgrade the battery size, or both. So if you want a faster, more robust, more stabilized, C1, it's pretty easy to upgrade that. The chassis is made out of steel. We could be using some kind of composite body for the interior as well. Parts count, we're 1/10 of a part of a car. Cars typically have around 24,000 parts. If you drive an Audi, it's 40,000. We only have 2,239. So it's pretty easy to manufacture. That's why we can make it affordable. In our audience, urban professionals, tech junkies, they have to have the first thing. They commute, they have professional life, they still want to have fun, and they want to have the first best thing, but at an affordable price.
You see from that video, actually, it's kind of a very cool application, right? I mean, it's like a motorcycle, but you don't need to know how to, balance the motorcycle, because the motor, that one will balance by itself, right? Use the feedback. They have some feedback mechanism. So you drive it like a car, but it's very small, like a motorcycle, right? So it's I don't know. Normally that the motorcycle, you don't have those covers, but here we design those motorcycle like a car. I think it's a pretty good idea. But the control system is a very key fundamental part for this type of application. You need to know how to make it stabilize by itself. So such that for anyone who only know how to drive a car can use it. You don't have to know how to ride a motorcycle, right? That is more complicated. You don't know how to have to balance the motorcycle by your skills, okay? But anyway, so for this one, what we give you the model, it can be a model that's a system with 6 state variables. There are 3 outputs, 2 inputs. Then I give you the design specifications. We say there is a overshoot, right? 10%, and then the setup is given has to be less than 5 seconds. All right, and then those are the formulas you can use to design the desired pose. But remember, right, there is no guarantee that the transit response will automatically satisfy the requirements if the pose are placed into the desired region designed by this formula, because this formula is only accurate for the second order system without any zeros. For the practical system, it's not second order, and it also has zeros. Then there will be a big difference. Therefore, you have to simulate the control system using Simulink and plot out the step response of the 3 outputs to verify whether the design specifications are met. So fine-tuning is necessary to get a good solution. Now, how to verify whether those specifications are met in Simulink? Since you are building the blocks with the Simulink, right, in MATLAB, it's easy to simulate the step response. For example, you first design the step feedback controller, right? U equals minus kx, you design your k using the power placement or LQR. When you want to check what the step response of the 2 outputs, actually 3 outputs, you simply apply U equals minus kx plus r, where the r are step inputs. Since there are 2 inputs, so you should apply only 1 step at a time and keep the other as 0, right? So there are 2 step signals. Then there are 3 outputs, right? So for each step input, there are 3 outputs. So in total, you are going to check the 6 step responses, right? And make sure all of them satisfy the requirements. Okay, is that clear? Then the first question, right? You assume you can measure all the 6 state variables. Sorry, there's some typo there. Then use a power placement, simulate the design system, show all the non-zero initial states. Then you need to use the transit performance to design the desired pose. But the desired pose might not meet the transit response requirements, so you need to vary the pose, mainly the pair of the complex pose, and find out which one can do the job. For this part, you need to check whether the transit specifications are made by using the controller, right? So minus kx plus r, where r is the step input. When try to simulate the step response, make sure the initial conditions are 0, right? We want to study the effects separately, the effect of the initial condition and also the step response. By definition of the step response, are the initial conditions supposed to be 0. Then you also study the response with a non-zero initial state, right? For that case, you set the external input r equals 0. And the initial conditions actually are already given, right, in the project. Also, you may observe, even though you have the same desired pose, you may get different results with different methods, because the different pole placement method will generate different zeros. Okay. The full rank method is usually better than the unit rank method. Okay, the second one is the LQR, right? Then for this one, you know, how do you solve the ARE equation? How to design Q and R to meet the design requirement? Since this is a 6-order system, right? You have to use the eigenvalue and eigenvector method. Of course, use MATLAB. Don't worry, if there is a problem in your final exam of LQR, right? The order of the system will be lower than 3, such that you can work out the solution by hand. There is no simple formula to relate the transit response to weight matrices Q and R. So you have to experiment, try and error, and find out the best one. For this part, you also need to check whether the transit response are made by using the controller, right? The same type of controller you are going to use, right, for the part 1. Now the third one, you need to design a state observer, simulate the resultant observer with the LQR controller, monitor the state estimation error, investigate effects of observer pose on state estimation error and closed loop control performance. Okay, here I think the student asked the question, right? The state is not available, right? How do we do that? Remember, you are doing the simulation, right? You are doing the simulation. So therefore, you can. In reality, the state is not available, but this is the simulation study. You can get the signals of the states. Okay. Therefore, you can monitor the state estimation error. All right, that clear? You are doing the simulation, and we are not saying the practical system. That's right. You cannot observe get the state estimation error directly. That's a good question. But you are doing the simulation, so therefore you know the true value. You can observe that. Okay. All right. For this one, you can build either a 4-order observer or reduced order. So when evaluating the performance, you only need to compare to the result where the states are all available, and in the case the initial condition is not 0. Because remember, of course, if the initial condition is 0, right, and also if your observer, the initial condition of the observer is also 0, your observer will match the state variable at the beginning, right? So there is no point to get the difference. So that's why no need to evaluate the step response for this part. You only need to study the behavior with non-zero initial conditions. Now, part 4. Assuming we're only interested in 2 outputs, right? Then therefore it becomes a 2 input to output system. Design a decoupled controller with closed loop stability and simulated set point response. Okay. So what after the decoupling is done, right, you have to answer whether is the decoupled system internally stable. For this part, you can try either state feedback controller or output feedback controller or both. When you check okay, how do you check whether the system is decoupled? It's easy. You set the reference signal. After the design, right, you set the reference signal as 1, 0 and 0, 1. Means that one of the input is 1, right? The other input is 0. Then if the system is decoupled, you should observe one output will change, the other output will be 0, right? If you don't observe that, which means that the one input will affect both outputs. It means that the system is not decoupled. So that is a simple way to check the system is decoupled or not, right? When you do this, you assume that the initial condition should be 0. Initial condition is 0. You look at the step response, you say one of the output will be, there's some response, the other output will be 0. Then you look at the other one step signal, you also look, okay, then the other output is, response, but the first output will be 0. Then you can conclude the system is properly decoupled. But then the last question is the decoupled system internally stable? For this one, right? You want to check whether all the state variables are stable when the initial state is not 0. So you just simulate the system, right? Without any reference signal, right? R equals 0, but the initial condition is not 0. Then you observe whether the whole system is stable or not. If it is stable, then it is stable. If it is not stable, then it is not stable. Also, we try to explain what you have observed. Okay. Okay, I think the solutions, to the first 4 questions, right, are straightforward. Just follow the design procedure from the lecture notes. Okay, now the question 5. Question 5, is about the server control. You want to design controller, right, to make an output follow the set point. Now the set point is specified in this way. Okay. First, you just assume you can measure all the state variables and design the server control. If you can do this, then the rest is simple. First, you assume that you know all the state variables. You make it work, right? This first step is important, because after this is done, right? You say, okay, now because I say you cannot measure all the state variables, you only have the 3 output signals, right? Just build observer. Yeah, build observer to estimate the state variables, and then you use those state variables, right, to replace those state variables in part 1. The controller not only can make all the outputs converge to the operating setting points, but also meet this transit specifications. You need to verify both transit specifications and the steady state requirements. Then you also should study, right, how the step disturbance can be rejected. Then for this problem, how do you add the disturbance? You just add the disturbance in this way as a load disturbance, right? You put a disturbance as an input signal. Okay, for this question, of course, there is a extra level because you have 2 inputs, right? But you have 3 outputs. But the 3 outputs, right, the set point are specified in a very special form. Right? You try to understand why is that in that form, and then when you directly follow by the way, you may realize some problem, but you try to think out a way to overcome these issues. It's not very difficult, okay? Then other objectives can be achieved. But this one, of course, it needs a little bit extra thinking to make it work. Now, question 6. So we learn about the multivariable interval control using state space model chapter 10. So that should be chapter 9. It's a classic way to solve the set point tracking, right? Now, in part 5, I specify the set point in a very special form. The way I specify it in this way, of course, actually is related to the solution to part 6. Part 6 means when I look at the set point, I don't use this formula to set the set point. I just use the set point, you know, there are 3 outputs, right? Y1, Y2, Y3. Those Y1, Y2, Y3, I just choose random values, let's say, arbitrary values. If that's the case, can you still make it work, right? You already make it work for the part 5. If you follow the same, can you make it work for arbitrary values of the set points? Okay. For those given set points, right, in part 5, let's say you already do it, but then you can try some other different set points to say whether it works or not. Or maybe you like to try other controllers, which are not limited to one covered in my lecture notes. After some attempts, you may get a conclusion. And to generalize a conclusion to arbitrary set point, you have to provide a mathematical analysis about your finding, right? Okay. This is the most difficult part of the mini project because the answers are not in my lecture notes. Okay, so extra efforts are needed to get it done. Also, there is no unique solution. Okay. Okay, in MATLAB, there are many commands for control system design, right? I already sent you an email about this, all those commands. You cannot use those commands in your report, say, okay, I get results using those commands, right? You can give me the design. But I also, of course, in the process of trial and error experiments, you can use those commands to speed up your search time experiments. Because if you try to get the solution right by hand for every possible experiments, it's too time consuming. So okay, no problem. You use those commands to help you. But once you find out, right, after many experiments, you find out some final design, the desired pose, or the final value of Q and R. For those final value, you have to detail the calculation step by step, following the design procedure in my lecture notes. Okay, you have to give me the details. In this step, you cannot say I use place, I use LQR, or I use care to do it. Okay, is that clear? But in the experiments, feel free, you can use them, or you try to verify your answer, you can use them. Okay. But remember, of course, for power placement, right? The place, the answer from the place, right, may be different from the the answer, you use other methods, like the 4-rank method, right? And then, because with 4-rank method, there are different ways to specify the desired controllable kinetic form. Okay. So you try to record the answer, right, by hand, and non-programmable calculator. Remember, right, in your final exam, you don't have MATLAB, definitely. You can have calculator, but you cannot use a programmable calculator. Okay. In this way, you will master the whole design procedure. That's the whole point. Right? I want you to know the theory, and I want you to know to do it, how to do it by hand. If you can only rely on MATLAB, come on to give you the answer, right? You will be in trouble in your final exam. Okay. No MATLAB in your final exam. Now you are recommended to use Simulink to get all those results, right? If you have no experience using Simulink in the past, you can learn it quickly. A simple way is to get familiar with Simulink by trying to reproduce some of the results showing the lecture loads. For example, the Simulink model for the servo control, right, actually is showing my lecture loads, right? You can just rebuild it, right? Try to build the block diagrams in the Simulink and see whether you can get the same result. And then try to play around with those blocks and see how to specify, how to change those parameters for each. That is a quick way to learn. Of course, some of you may already have some rich experience using Simulink, right? You don't have to do this. Okay. When you do the simulation, another important thing is to use format long in MATLAB. Okay. That will increase the numerical accuracy. The results from most of the numerical methods are not precise. So for example, instead of 0, you may get something like 10 to the minus 14. Then you treat them as 0. And also sometimes, right, it's supposed to be a real value, but you may get some complex value. But you can see, okay, in those complex value, actually the imaginary part is very small, right? In those cases, you can just assume that those imaginary parts are 0. Okay, that's the way of how you deal with the numerical errors in MATLAB for this project. Okay. Now some tips for the final exam. First of all, right, remember there are for all the modules, right, normally but not all, some of the modules that don't provide the past exam papers. But for this one, we do have this one, right? You go to this website, library, you know that there are exam papers, right? You search, right? You can just log in. There are some past exam papers, okay? Then you can find, and then that will, of course, you have some sense about what kind of questions, what types of questions may appear. Okay, there will be 2 questions from my part and also 2 questions from part 1. If you can work out the solutions to the first 5 questions of the mini project, right? I don't require you to get the solutions for the question number 6, right? As I said, that needs some extra thinking or work. But you try to get the answers for the tutorial questions by yourself. If you can do it, you are guaranteed to score high for my part. So the difficult level, of course, of my exam questions will be comparable to those tutorial problems. Okay, it cannot be higher than that. Definitely it will be much easier than the problems for your mini project, right? You are not going to deal with a 6-order system. Again, so because we have, many topics, right? We have 5 topics. So due to some topics will not be tested in the exam paper. Okay. But however, all the topics have equal probability to appear in the exam paper. Now, some students like to use the past exam papers to bait. Some topics may never appear. Don't do that. Don't do that. There are some other tips. So of course, we are well aware of the time constraint of the final exam, right? It's 2.5 hours. Therefore, we set the question in such a way that the numerical calculations are simple. Okay. If your solutions, found out your solutions are very complicated and tedious, then something must be wrong. That is a signal. Say your solution might be wrong. Okay. Now the second one, if you don't know how to solve a problem, right? You don't leave it blank. You try to, let's say, copy some formulas or whatever, write something there. Normally, the professors are very lenient. All right, they will try to find marks for you. If you leave it blank, right, they cannot give you marks. It's blank, they cannot give you marks, right? If you write something, you may get some marks, even though you don't know how to solve the problem. Okay, that is the tip. Don't leave it blank. Okay, and then the exam is closed book, but you are allowed to bring one A4 size help sheet. Okay. The help sheet can be double-sided. Can be double-sided. Then you can handwrite or print. Either way, it doesn't matter how small you print, but you cannot bring a magnifier. Now, when you prepare your help sheet, the Laplace transform, you don't have to print. The Laplace transform table will be provided in the exam paper. So we know that will take a lot of space, right? You don't have to print that out. Okay. You don't have to take a picture. All those things will be given to you. All right. Finally, I think we still have some time, right? It's time for questions and answers. Okay. Any questions? Where was the final exam? When? I mean, it is. Okay, I think it is in the Monday after the recess week, right? November 21st, I believe. The next week is recess week. And after the recess week, the Monday, okay? You can check, it is in Canvas, you can check the date. Any other questions? The location? Or you all know that, right? I think you should. I mean, the location is not definitely not here. I think it's in the. There will be two places. Just over there, like in the engineering auditorium and the RT7A, I believe. Okay, I think okay, if you don't have any question now, and you can ask me the question later. Probably before the exam, I will arrange a clinic session, a Zoom session, so you can ask me questions over those clinic sessions before the final exam. Okay. Any other questions? What is what? Oh, okay. The student talk about the theory. The theory. So I don't know. I mean, this is first time have over 200 students. The fail rate is quite small. So normally in the past, right, the students, if the students given to the easy one, but in the third class is one, right? And a very rare thing, but it happens, right? You know, the class are being public, but somehow two reports match each other. So both of them get 0 marks. In that case, they cannot pass. Remember, why do I set the design parameters as your metric completion number? We have a purpose, so it's easier for us to find two identical answers. Okay. Sometimes, right? Let's say you are a good word, but you follow square of the word, like don't copy out, otherwise the word is being trouble. So we don't distinguish who is copying who. Both of them will be penalized. Okay, and normally for students who can do the mini projects with most of them will pass. Okay, so the failure rate is very small. Pass is F. Of course, there is a for the course, right? A, B, C, D, F. F is pass. E still is already pass. F is fail. No. F means fail. D, right? D means of course your pass. D and D pass. And then you see D is the pass, D is the pass. Any other questions? How many people get A? Well, I think the average rate is it will be average rate okay. So there will be a large number of students who will get A and A minus, right? Or if you get a B plus, right, which means close to the average, probably a little bit above the average. Okay. But below B, of course, you are below the average. Another question? I know you don't want to ask me questions in the class. You want to ask me questions after the class is over. All right. Okay. Anyway, so this is it, and thank you. So there are no more class next week, but if you have any questions, always drop an email. We can always to answer the question.